This lecturette covers the areas of pH titration curves, pH titrations, the idea of alpha plots, which is the preponderance of an acid or a base of a weak acid-base pair based on pH, the use of pH indicators and why one indicator is used as opposed to another, and we'll look at a couple of special acid-base systems, the carbonate system as well as amino acids. So we're going to start out by looking at pH titrations. The idea of titrations is that you have one unknown sample and one known sample, and you react them together. In this case, we're going to use pH as a method both of determining the concentration of the analyte, the thing that you don't know, as well as saying something about its acid-base strength. And so what we really want to do is look at the curves that one gets for doing an acid-base titration. So we're going to look at a reaction of HCl being added, having to an HCl solution aqueous. We're going to add a strong base, sodium hydroxide. What we're going to do is we're going to start with 0.10 molar of this, and we're going to add 0.10 molar sodium hydroxide. And of course, the products are water, liquid, and sodium chloride aqueous. It's important to note that both of these are pH neutral. That'll be important in a couple minutes. Okay, what we're going to do is we're going to make a plot of pH on our y-axis and milliliters of NaOH solution added. And let's say that we start with 25 milliliters of our 0.1 molar HCl solution. We'll make that 7. We're going to make that 1. We're going to make that 13. So we start with 1 molar, 0.1 molar HCl solution. That has a pH of 1. So it starts out as a pH of 1. And what will happen is, as we start reacting, what will happen is the HCl will decrease as we add up the NaOH. As it reacts, you make water and NaCl. So what happens is, as the titration goes along, as you're adding NaOH, you're decreasing the concentration of HCl. And so what will happen is the pH will go up. But it'll go up pretty slowly because of the log nature of pH. We're going to put that as our 25 milliliters there. And what happens is, as you approach the end point, the equivalence point of the titration, what will happen is you're just about out of HCl. And at the equivalence point, when you've used just the same number of moles of HCl and just the same number of moles of NaOH, you've totally expended both of these, so there's no longer an acid nor base in solution. You just have a solution of just water and sodium chloride. Both of those are pH neutral, so at the equivalence point, you will have pH of 7. After you've reached that point, if you keep adding in NaOH, what happens is you're adding the strong base into a solution for which there's no more HCl left to react. And so for all along here, you have excess HCl. At this point, you have neither excess HCl nor NaOH, but beyond that, you have excess NaOH, so the pH will steeply go up. And so over here, you have excess NaOH. And so one of the important things to note here is that for a strong acid, strong base titration, where strong acid is being titrated with a strong base, just to make sure that you've got this down, you've got your burette here, you have your flask, you have your HCl solution here, and you have your sodium hydroxide solution in here, and that's being added into there. And so that's what the titration curve looks like for that. As we'll talk about later, what you'll want to do is you'll want to use if you're using a pH meter, you can just measure that, that's fine. But if you're using a pH indicator, you want one where the color change happens in this steep area. Okay, so next we're going to look at the reverse, where we're going to have in our solution, we're going to have a strong base, NaOH, and we're going to add to that an HCl solution. So it's the same idea. That what you have is you have pH here, and we'll put 7, we'll put 1, we'll put 13. We're going to have 0.1 molar NaOH, and to that we're going to add 0.1 molar HCl. and the reaction is the same because it's the same compounds, of course. You'll make water, and you'll make NaCl. And again, both of those are pH neutral. So at the equivalence point, again, we would expect to have no acid nor basic properties. So you'll have a pH of 7. So when you start out with just 0.1 molar NaOH. That has a pH of 13. As you start adding HCl into it, you start consuming the NaOH, so the solution becomes less and less basic. And so as you go along, the pH starts decreasing because you're making the solution less basic, but slow again because of the log nature of pH. But then we expect at the equivalence point, at 25 milliliters, that the pH will be neutral, 7, because when these are both just used up, you'll have a solution of water and sodium chloride, both are pH neutral, and so this will come diving down really fast, and then go something like that. And so that's the pH titration curve for a strong base to which you add a strong acid. So it's basically the inverse of what we saw for our strong acid, strong base titration. So here at the beginning, you start with an excess of sodium hydroxide. At the equivalence point, you have water and NaCl. And beyond the equivalence point, you have an excess of HCl, which is why the pH gets really low, because you're now in an acidic solution. Okay, those are both pretty easy. Now let's look at a pH of a weak acid with a strong base. And so for this one, we're going to use, I believe this is probably, I'm not sure what acid this is, but we're going to do a general acid, HA plus NaOH is going to make NaA plus water. And so we're starting with a weak acid, and we're going to start with it at 0.1 molar. And we're going to add 0.10 molar of NaOH solution. And in this case, we're starting with 20 milliliters of this. And so our equivalence point is where you use the same, because we have the same concentrations, it'll be where the same volume is. So the equivalence point will be at 20 milliliters. So that's the equivalence point, which is the end point. Now what happens here is that when we have 0.1 molar weak acid, the pH is above 1 because not all of that ionizes in solution. So a certain amount ionizes, and you start with a solution that's acidic, but not as acidic as if it was a strong acid. And you go along, and as you go along here, you have excess HA in solution. Now the important thing here is that what happens is, again, here you have excess HA. Here, at the equivalence point, you've used up both the HA and the NaOH. And so now what you have is a solution of water, which was already there, of course, and NaA. And let's write that down as Na plus A minus, the conjugate base of the weak acid HA. And beyond there, you've used up all the HA, and beyond there you have excess sodium hydroxide. So the solution is much more basic. Now notice here that at the equivalence point, at the end point, the pH is greater than 7. And the reason for that is at the end point, I'm using the end point and the equivalence point interchangeably. At the end point, the solution contains A minus, which is a weak base. So the solution is slightly basic, weakly basic at the equivalence point. Okay, now that's pretty cool, and it makes sense, but there's something even cooler, and that is we can use this portion of our curve to say something about the strength of the acid HA, which we don't even know what that acid is. And to do that, we're going to use the Henderson-Hasselbalch equation. And the Henderson-Hasselbalch equation is that pH equals pKa plus the log of the conjugate base concentration over the conjugate acid concentration. The thing that's really neat is when the conjugate base concentration equals the conjugate acid concentration, then the log of the base over the acid equals 0, because the log of 1 is equal to 0. So if these two are equal to each other, then their ratio is equal to 1. The log of 1 is 0. So at that point, the pH equals the pKa of the weak acid. And so if we knew where that was on this curve over here, we could determine the pKa of the acid, and therefore the Ka of the acid. And so it turns out that at here you have 100% HA. You have all of it before you've reacted. At the end point, you have 0% HA. You've used all the HA up. That's the whole point of the equivalence point. It's where you've used it all up. The place where you have half of it gone is at the midpoint. At the midpoint, 1/2 of HA is not just gone, but has been converted to A minus. And so at the midpoint, the concentration of HA equals concentration of A minus. And so this is the big take-home message. At the titration midpoint, halfway between where you start and where the equivalence point is, the end point is, halfway there, the pH at that point is going to be the pKa of the weak acid. The pH of the solution equals the pKa of the acid. So in this particular case, I'm going to erase that because it's a little hard to see here. Whoop, get back there. If we just go across here, you can do it a little, experimentally you do it a little more carefully than this, but let's say it's around 3.5. So for here, the pH at the midpoint equals 3.5. So the pKa equals 3.5, and even better, the Ka for that acid is equal to 10 to the minus 3.5, which is equal to, what is that equal to? .2 times 10 to the minus 4. And so this is one of the main ways people find Kas, the Ka values that you see in tables. They're largely found by doing your titrations and finding the midpoint of the titration. That's the best way to do it. Okay, that was really neat. Okay, now we're going to look at a more complicated system. We're going to look at a polyprotic acid, and we're going to look at the carbonate system. So the carbonate system involves carbonic acid, H2CO3. That can lose a proton to make hydrogen carbonate. It's also called bicarbonate ion. And that can lose a second proton to give the carbonate ion. And it turns out that each of these has a different Ka, each of these two steps. So the first step is Ka1, the second step is Ka2. And so Ka1, if we write out our equilibrium expression for that, it's going to be products of reactants. It's going to be HCO3 minus times H3O plus over H2CO3. Ka2, on the other hand, is going to be, and that equals 4.2 times 10 to the minus 7. So it's a pretty weak acid. Okay, Ka2, our acid now, our reactant, is the hydrogen carbonate ion, the bicarbonate ion, and our products are going to be CO3, 2 minus, times H3O plus. Okay, now, the first question is, what's the pH of the solution? So the pH of the solution is going to be minus the log of the H3O plus concentration. And that's going to need to be found. We need to find the hydronium ion concentration. And so notice that the Ka for the second reaction is 4.8 times 10 to the minus 11. So this is pretty weak. This is very weak. And so what we can do is we're going to assume, and it's a good assumption, assume that the second reaction does not contribute much H3O plus. And that's actually true for two reasons. One is that what happens is for the second reaction, the Ka is actually really quite small, but in addition, for the second reaction, you already have a fair amount of hydronium ion, which is going to suppress the second reaction going forward due to Le Chatelier's principle. So for two reasons, we know we're not going to make much more hydronium ion concentration. So we can determine the H3O plus concentration using just the first reaction, and so we do that just as a standard acid-base, a standard weak acid reaction. So we're going to make we'll do a quick H2CO3 plus water goes to make H3O plus HCO3 minus. Our initial is going to be 0.10, 0 and 0. Our change is going to be minus x plus x plus x. Our equilibrium is going to be 0.10 minus x, x and x. And therefore, we can say that Ka, 4.2 times 10 to the minus 7, is equal to x squared over 0.10 minus x. And because Ka is so small, we can assume that the 0.1 minus x is really just very, very close to 0.1. That's a very good assumption. So that equals x squared over 0.10. So therefore, x is equal to the square root of 0.10 times 4.2 times 10 to the minus 7, which is going to equal 4.2 exponent 8 minus, I'll take the square root of that. That comes out to 2.04 times 10 to the minus 4. Fourth molar. And therefore the pH equals minus the log of 2.04 times 10 to the minus 4, which equals 3.69. Okay, so that's the first part. Now what we want to do is we want to look at the second part of this reaction. And to do that, let's remind ourselves that X here is the concentration of the hydronium ion and the concentration of the hydrogen carbonate ion. So let's look at, I'm going to go to a blank screen. So for the second step now, we want to find out what the carbonate ion concentration is for this system. If we've started with 0.1 molar of carbonic acid, we know we made 2.04 times 10 to the minus 4 molar of our hydrogen carbonate. And we also know we also made 2.04 times 10 to the minus 4 molar hydronium ion concentration. So in the second step, what we have is we have the hydrogen carbonate now is going to react with water in the second step of the diprotic acid deprotonation. And so that's going to make a little bit more hydronium ion. We already said we think that'll be small, and we'll see that it is. Ooh, that's cool. And then we're going to make hydronium ion, and we're going to make carbonate ion. So our initial concentrations for these are going to be the 2.04 times 10 to the minus 4 molar that we made to start after the first reaction. The hydronium ion concentration is also already 2.04 times 10 to the minus 4, and our initial carbonate is 0. And our change here will be how much of this hydrogen carbonate reacts further. So that'll be minus x. You'll make a little bit more x of hydronium, and you'll make x amount of carbonate. So our equilibrium concentrations will be 2.04 times 10 to the minus 4 to minus x of the hydrogen carbonate, the bicarbonate. And you'll have 2.04 times 10 to the minus 4 plus x of hydronium, and you'll have x of the carbonate. And so then, as we do for equilibrium systems, we're going to plug these numbers into the equilibrium expression. So Ka2 is equal to 4.8 times 10 to the minus 11, and that's going to equal the hydronium ion concentration times the carbonate ion concentration over the hydrogen carbonate concentration. And so that's going to equal 2.04 times 10 to the minus 4 plus x times x over 2.04 times 10 to the minus 4 minus x. Now notice that the Ka here is really tiny. It's really, really small, which means that this second reaction is only going to go a tiny bit. It's going to go hardly at all because that's such a small number. And because you're actually starting with some of the product, you're starting with some of that in solution, the hydronium ion, so it's going to suppress the reaction going forward. So because of that, both the 2.04 times 10 to the minus 4 plus x and minus x can ignore the plus and minus x. So we're going to have 2.04 times 10 to the minus 4 times x, that x is the carbonate ion concentration, over 2.04 times 10 to the minus 4 without any x. And this is so cool, the concentrations there go away, and x equals Ka2, which equals, in this case, 4.8 times 10 to the minus 11 molar. So that is the carbonate concentration when you're done. And that's generally true of weak diprotic acid systems, is the concentration of the second product, the second base, when 2 hydrogens have been released, is in fact equal to the second ionization constant. Okay, now the next thing we're going to do is we're going to look at a titration curve for a polyprotic acid. And so I think that this one is for oxalic acid. H2C2O4 goes to make HCO2O4 minus, which then goes to make C2O4 2 minus. And so what happens is this first step involves one K, and the second step involves another K. And so there's 2 titrations that go on. The first titration has, we start here with H2C2O4, and in the first titration, this here is the equivalence point, the end point. End point number 1. And so at that point, the solution contains, you've done the first reaction 100%, and so you now contain hydrogen oxalate. And so during this portion here, you're converting H2C2O4 to HC2O4. So during this time, you've got a mixture of these two, so you have a buffer solution. There's a buffer solution during that time, and the midpoint, pH, there, equals pKa1. That is the Ka for taking off the first hydrogen. Okay, the second step is you're now taking off the second hydrogen. So now hydrogen oxalate is losing its hydrogen to become oxalate. It's being taken off by the base that you're adding. And so you now have another buffer. It's a different buffer. It's a buffer between hydrogen oxalate and oxalate. And the second equivalence point or endpoint is there, where you've used up 100%. You've now done 100% at this point here. You've done 100% of the second reaction, so now you have oxalate ion. And the midpoint here, the second midpoint, is pKa. The pH there is equal to pKa2. That's the pKa for the second step coming off. And so because you have two inflection points here and here, you know you had 2 different hydrogens coming off. So you can tell actually quite a bit about the acid-base properties of even relatively complicated molecules by looking at their titration curves. Much, much more than you can while figuring out the concentrations. And in fact, what's really neat about this is, for both this example and these examples here, is you don't even actually need to know the concentration of the acid or the base. You just need to know where the endpoint comes in, and you know right at the middle of that is the equivalence point, is the midpoint. So you can figure out the pKa of the acid without even knowing its concentration or what it is. It's a cool thing. All right, the next thing we're going to talk about is we're going to change gears. And what we've been talking about so far is the concentration of the acid and or the concentration of the base control the solution pH. That's everything we've talked up till at this time. But for lots of solutions in the real world, the pH is set by the fact that you've got a bunch of acids and bases in a solution, but you've got some other compounds in there that have acid-base properties. And so in this case, now we're going to talk about it, is the pH controls the acid and the base concentrations. So we'll look at our Henderson-Hasselbalch equation again. So the idea here is that up until now, we would know these two things. And if we knew these two things, we knew pKa, you could figure out the pH. Now what's going to happen is you're going to have a solution for which external acids and bases, some other buffer in solution, is going to set the pH. And when the pH gets set, some other acid-base system you have in there, its acid and base ratio will change so that it reaches equilibrium. When you're at equilibrium, this equation is true. So that's what we're going to be doing. Okay. So what we're going to do is we're going to look at a system for HF, hydrofluoric acid. So hydrofluoric acid has a Ka of 7.4 times 10 to the minus 4. Its pK is 3.13. And so as we saw before, when the concentration of the acid equals the concentration of the base, in this case HF and fluoride ion, then the pH equals the pKa of the acid. And so if we had a pH of 3.13, which is the pKa, then the base to acid ratio would be 1. And so that means it would be 50% HF and 50% F minus. If we had a pH that was 1 pH unit greater, it's lower than this, the acid would be 10 times bigger. So now what you would have is you would have a ratio of 0.10 of base over acid. And if you had a 2 pH units lower, you would have 100 times more base over the acid, so it would be 0.010. On the other hand, if you were 1 pH unit more basic than the pKa, it would be 10 times as much base. And if it was 2 pH units greater than the pKa, it would be 100 times more base than acid. And so what we do is we make something called an alpha plot. And an alpha plot is a plot that shows the preponderance of the acid and base forms as a fraction instead of as a percent. And when you do that, what you see is this is the pKa here. And below the pKa, you have mostly HF. So this is the HF fraction. And this is the F minus fraction. So when you're below the pKa, there's more acid than base. When you're above the pKa, there's more base. And each step is like a tenfold change. So when you are 1 pH unit above the pKa, you've got about 90% of the base and about 10% of the acid. When you're 1 pH unit below the pKa, you then have about 90% acid and about 10% base. And when you get about 2 pH units in either direction, it's about 99% and 1% for each of them. Okay, and so the big picture here is that what happens is if you are above the pKa, this acid-base system, which can either be HF or F minus, is mostly in the F minus form. And when you are below the pKa, significantly, it's in the acid form. And so if you have some external acids and bases in your solution controlling the pH, but you've still got this stuff in here, it'll be converted into either the HF or the F minus forms, depending on whether that solution is basic or acidic. Not basic or acidic in terms of pH 7, but in terms of the pKa. All right, so let's look at, let's move on from that. Let's look at another example. If you had pH, like this example, let's look at an example of this. If the pH was 4.9, in what form is the HF system? Is it HF or is it F minus. So what you do is you say, there's two ways. You can do it numerically. So 4.9 is greater than the pKa of 3.13. That's the pH, that's the pKa, and so therefore the concentration of base must be greater than the concentration of the acid because you're more basic. If you look at our plot, you're right about here, you're on 4.9, so you're right about here. So you've got about like 95% of the F minus. That's the F minus there. And this is the HF here. And you've got maybe like 5%. I'm just guesstimating from the plot of HF. So because the pH you have is greater than the pKa of 3.13, you're in the F minus domain. And if this question had asked what would it be at like 2.0, then it would be the HF domain. Okay, so let's look at an alpha plot for a system for which the acid had a pKa of 9. So Ka was equal to 1.0 times 10 to the minus 9. Let's say about that. In that case, this would be where the system would shift over. So before then, you'd have almost all HA. That'll be our acid. And above that, you'd have A minus. And it would be 50-50 at pH 9. So it'd be like that. And it'd be like that. So above pH 9, you'd have A minus. Below pH 9, you'd have HA. So notice, if you had, let's say, a solution that was pH 6, at pH 6, this acid would be in the acidic form. This acid-base system would be in the acidic form at pH 6. Whereas in the F minus, HF F minus at pH 6, it would be in the basic form. So at a single pH, you can have one acid-base system exist in its acid form, where a different acid-base system exists in its basic form. All right, let's look at the alpha plot for our carbonate system we looked at a couple minutes ago. And to do that, we need to know the pKa's for these two different systems. And so the pKa for the first one is minus the log of 4.2 times 10 to the minus 7. Which is 6.37. 6.38. And the pK, that's pKa1, and pKa2 is 10.32. So I'm going to draw a line around 6.3, so that's a line there. Another line at 10.32, which would be right about there. So what happens is, in this region, we're going to have carbonic acid, H2CO3. In this region way out here, we're going to have carbonate ion, CO3 2 minus. And in the middle region, we're going to have hydrogen carbonate ion. I'm going to write this up here for reasons you'll see in a moment. And so what happens is the first conversion from carbonate to bicarbonate happens at, it's 50-50 at the first pKa. So that goes down like that. And this goes up like this. So I'm going to stop here for a second. This is going to be the hydrogen carbonate solution. The second conversion from hydrogen carbonate to carbonate is going to happen and be 50-50 at 10.32. So the carbonate's going to be low up until here. So that's the carbonate concentration. It was 0 all throughout here. The hydrogen carbonate is going to come up here, but it's going to come back down again and go down there. So the hydrogen carbonate grows in from the first reaction, which is half done at 6.38, but as the pH increases after 6.38, it grows up. But then, as you get further in pH, then the hydrogen carbonate then reacts to make the carbonate, and it's 50% gone by the time you get to 10.32. Okay, so then our next question would be, at what pH would you expect to have a lot of hydrogen carbonate around? And so we're going to go back to our plot here and see that it's going to be between, you're going to have hydrogen carbonate around pH 7 and around pH 10. Roughly that range there is when you have a fair amount of hydrogen carbonate. Okay, the next thing we're going to talk about is pH indicators. So pH indicators are in fact weak acid-base pairs for which the acid and the base have different colors. So they're just special weak acid, weak base systems. So they basically work just like any other weak acid, weak base, except there's a color difference between the two. And so what happens is if you wanted to have a pH indicator that changed at, say, around 9, what you would do is you would look for something that changes color around 9. And what that means is where it changes color is this is the base form and this is the acid form. And so the pH change happens at the pKa of the indicator. So if you had an indicator that essentially went like this and converted over at pH 9, so that was the HA and this was the A minus, that would be a pH indicator like thymolphthalein. If you wanted one that was actually a methyl orange, which would be over here, I'm going to just erase these things here. Methyl orange, on the other hand, methyl orange changes color around pH 4, so it would be like this. And so you would have A minus over here and HA here. So pH indicators are compounds people have found just empirically, just by finding them, trial and error, discovering them, for which the color changes happen in different places. The trick here is that you want to choose an indicator that changes color at the right pH. And the right pH is not the pKa of the weak acid you're doing. This is titration of HClO. You want to choose one that happens, where the color change happens at the inflection point, at the end point of your titration. So in this case, you want to be somewhere around here. So that's 7, 8, 9, 10, around between 10 and 11. And so a good pH indicator would be something like the ones right near the bottom. So it'd be like alizarin yellow would be about the best one here. Or you could use, better than that, actually be thymol blue. So thymol blue has a color change here. It must be a diprotic acid because it has 3 different colors. So thymol blue would be a good one because it's going to change right around 10.5, which is right about where that inflection point is. Okay, our last subject we're going to talk about is amino acids. So amino acids are diprotic acids, and there are 2 acid groups on most amino acids. One acid group is an NH3 plus group, which goes to make, it loses a hydrogen ion to make an amine group. And the other one is a carboxylic acid group, which is COOH, and it loses a hydrogen ion to make a carboxylate group, COO minus. The pKa for these is generally somewhere around 9, and the pKa for these are somewhere generally around 5, roughly, or even lower than that. So in this particular case, it's even though it's around 2 or 3, so or around 3. In fact, I knew that they're around 3. Okay. Now, so what happens is if you have a very low pH. A very, very low pH. So let's go ahead and draw an alpha plot for this, actually. 7, 13, 0. We'll put in our pK of 2.34, so that's about here, 2.34. And then we'll put in our second pK, which is around 9.6. 9.6. And so what's going to happen is we're going to start with both the nitrogen-based acid and the carbon-based acid protonated in their protonated form. And when you pass 2.34, what will happen is the stronger acid will lose its proton, lose its hydrogen ion. And the lower the pKa, the stronger the acid, so the proton comes off the carboxyl at first. So that's an alpha of 1, that's an alpha of 0. Remember, that's the fraction of the acid or base forms. So this is the COOH becomes COO minus at that stage. So in the middle place, when you get to pH 2.34, you have 50% of the protonated carboxylate and 50% of the 50% of the carboxylic acid group and 50% of the conjugate base of that, the carboxylate ion. Okay, now as you go more basic, what will happen is when you're around pH 7, I'll redraw my alpha plot here. 1, 0, 7, 13, 0, 2.3, 4, and around 9.6. So at this stage, what you have is at pH 7, you have, well, as you went along, this is the COO minus group. This is the COOH group going down. And then as you approach 9.6, the second hydrogen comes off, which is the one that comes off the ammonium ion. And so what will happen is when you are right here at 9.6, what occurs is you have taken half of the ammonium ions, hydrogens, and lost those, and half of them are remaining and half of them are gone. So at this stage right here, you have 50% where the amino acid has a COO minus plus an NH3 plus group, and 50% of an NH2 group and a COO minus group. When you get to far over here, what you've done is you've lost both of the hydrogens. So now you've got the COO minus group plus the NH2 group. Now, one thing that's really neat about, and so you have an alpha plot that looks like this. So this part here is COOH plus NH3 plus. This here is COO minus plus NH3 plus. This part here is COO minus plus NH2. So notice this middle section here. This middle section here is overall neutral in the sense that it has no charge. It has a negative charge there and a positive charge there, but it does in fact have charges. That is called a Zwitter ion. A Zwitter ion it's mainly used in carboxylic acid. It's mainly seen there, where you have a compound that in solution has a positive site and a negative site, but overall is neutral. Okay. Finally, we're going to talk about what's called an isoelectric point for amino acids, and that is the point at which the compound is neutral. And so the isoelectric point for this amino acid is this region here, and so it's the place where you're halfway between that pKa and this pKa. That's the isoelectric point, where you'll have the highest amount of your neutral compound, and if you have any of the other two, they would be in equal concentration. All right, and that is the end of section 17.3 and section 17.2.